Yes, sir.
Okay. Okay, good afternoon. Let us start now. So welcome you all to session 13. We have 1 week to go. So let me tell you what I plan to do this week. I want to cover two things in detail. One is today's class, and one more thing is maybe tomorrow or day after about cache coherence. Okay, scoreboarding and cache coherence. I will explain in detail, and there will be some good questions also from these topics. And then I want to cover other topics without going into the details, just giving you overview so that you heard of these terms somewhere so that you can go deeper into it later on, because we don't have time. We have only 1 week. So I cannot go and explain everything in detail to make you understand at the implementation level. My aim is to at least make you aware that these are the things which are happening in the architecture. You don't know the implementation, but you know what it is doing, but you may not know how is it doing. Okay, so that's my plan. So today what I want to do is cover this scoreboarding in detail, and pay attention to this. I am having a simulation here. You will be able to understand it clearly, and I'm going to have some questions on this for sure. At least I'm planning of giving some 10 marks. I don't know how 10 marks out of what. So today's session is going to be important for you to get this. Okay, fine. Let us see what is scoreboarding. Scoreboarding is a way of doing the dynamic instruction scheduling in the hardware. Last class we covered how dynamic scheduling to be done by the hardware impacts other stages prior to that. Okay, so what are the stages? First stage is instruction fetch and then decoding. So these are the two stages before we come into instruction scheduling. So I told you something which are happening in this stage, because after this instruction decoding we want to issue different instructions, and we have different functional units. We want to make use of these functional units as much as possible so that we have sufficient instruction here to schedule them on the different hardware what you have. Now, if we need to do this, we need to do something prior to that. Suppose if you are invited 100 people in your house for a party, you have to make sure that you have cooked sufficient food to feed all of them. Okay. At the same time, some food you will be making it like puri, you will be making it while the guests are there at home. So you have to make sure that that is being done at the same rate as people are consuming it. So we need to make sure that instructions are available for us to make use of these functional units. What do? We have to fetch more instructions. That means you cannot say I will fetch one instruction per cycle. You have to fetch more instructions. Fine. But if I fetch more instruction in a cycle, I have to decode them also. More instructions I have to decode so that I understand which are the instructions are likely to be executed by this functional unit, which are the instructions are going to be executed by another functional unit. So I need to decode them fast. So I talked about pre-decoding. While fetching the instruction itself, find out what type of instruction it is. That is called pre-decoding. And then come into the decoding stage where you will know what are the operands, where are the destination registers, where is it going, and what are the dependencies. Dependencies you don't do here, you do it somewhere here. So you understand more about the instruction in the decoding stage. And then we issue the instructions. Now, why do we have a issue stage instead of executable stage? In the original pipeline, IF, ID, EX, MEM, and then WB, right? So in the EX stage, we cannot directly from ID stage, you can go into EX stage because we got to do some job. There is not only one ALU now executing the instructions. There are many functional units which can be fed different instructions. So we need to do something prior to that. That is the job done by splitting the ID stage into two more stages. I will talk about it now. Okay. And then we'll start executing the instructions. Now, let me not cover too many things here. I told you what all needs to be taken care of. Okay, let us go into the details. Scoreboarding is a technique to allow instructions within a basic block. Okay, now I'm talking about basic block because these are the instructions which are going to be in a sequence and all of them need to be executed. Remember, basic block means all the instructions have to be executed in the sequence they have come inside, which is given by the programmer. Now, what is above the basic block and what is the end of basic block? Maybe some jump instruction or maybe a call, function call, or maybe some instruction which has jumped from somewhere and has come to the entry of the basic block. It has come from somewhere, we have jumped from somewhere and entered there. So this is the starting. From where we are coming, we don't care. This is the basic block mean. These are the instructions which are to be executed together without any missing out anybody, any of those instructions. Now, once you have this basic block of instructions and we have a set of functional units, different type of instructions would be there in this basic block. Now we want to use these functional blocks which are there to run these instructions on them. So as I told you, a set of instructions will have dependencies because one register will be written by destination. Now one instruction will be computing something and writing into a register, and that value will be required by the next instruction. So these kind of dependencies are there, and we saw three dependencies, data dependencies. We don't care about the branch instructions. Control dependencies, control hazards, we don't care because we are only talking about basic blocks between two control flow instructions, maybe. So there are no control flow instructions coming in the basic block. Then it cannot be called as a basic block. Basic block means instructions which are either arithmetic operations or memory load store operations. That's all. Arithmetic operation may be a logical operation as well as integer operations or floating point operations. It could be anything, or even compare operation could be there, but there is no jump instruction or jump on carry instructions. We are not taking care of those instructions here. Basic blocks means only instructions which are doing some processing with registers and maybe doing a memory access, memory store, memory load. That's all. Okay. Now you have to keep these things in mind clearly. Okay. Now scoreboard, I told you this. These are some names given because of the initial architecture, which was where it was implemented. It was called scoreboard. Don't worry about it. Now let us come into this. Except read after write. Read after write. What I mean by read after write, some instruction is writing into destination register. Okay, this is one source. This is another operand. This is a destination register. Some instruction is calculating something and then writing into this register. I have to read it after this write has happened. That means some instruction wants some operand which is coming from here. Same register. I'm saying this register and this register names are same. So I need to read this operand only after this write is done. This was the data hazard which was in pipeline, and we handled it by using forwarding technique. These two were not there in the pipeline. What are they? This is write after read. That means, let me explain that. Some instructions are there. Assume this is one register R1 which is getting written. Assume there is one instruction here above it which is reading from the register R1 because it is the operand. It should read something here, and then do something and then put the result. Now this reading of this operand should happen, or the other way, the writing of this register should happen after this reading is done. Right after this reading was done by the previous instruction. Please remember previous instruction in the sequence. Now in the pipeline, if you remember, operand reading is coming first and then writing results are coming next later on. So if suppose this is the instruction, I call it as I plus 1 is in the write operation, means the previous instruction would have even completed its execution. Forget about reading, it has even completed it in the pipeline architecture. So write after read is not possible in a normal RISC pipeline. Okay, so we were not worried about this particular hazard at all during the pipeline stage when we were implementing the instruction execution using only pipelines. There was instructions were executed in the sequence. There was nothing out of sequence. Now we are talking about dynamic instruction scheduling. That means instructions are scheduled out of executed out of order. I have to be very careful. Instructions are executed out of order. That means there is a possibility that this instruction is not even started executing, but the next instruction has started executing as well as completed the execution. That means this addition or whatever operation has been completed. Now it wants to write into R1, but previous instruction has not even started. It has not even started. That means this does not even read the operand. Now, if I allow this write to happen, I will not have the old value which was there prior to this instruction. So I have to take care of write after read. I have to wait for writing this value till the reading of this register done by the previous instruction. Why is this happening? Because of out of order execution. I can execute this instruction without waiting for the previous instruction to even start. Forget about even completing. Before even it starts, I can execute this instruction and complete it also. But I cannot write the result. The same register will be affected. If I write the value, you remember there is only one R1 in the system. I am assuming a single core and it is executing the instruction. There is only one R1 physically there. If I write the value, a new value, which is here computed by this instruction, the old value which was there in R1 required for this instruction is lost, permanently lost. So I have to take care of it in the dynamic execution. Now what is wow? So let me erase all this. Suppose I have an instruction. It is computing something from here, writing into it. This is also computing something from these two and writing into it. Now imagine I have the same register which is here as well as here. I have two instructions, okay? One is computing something and then writing into it. Another one is computing something and writing into it. Now, again, if I assume this instruction is starting and executing ahead of this instruction. Now, what happens? I have this value which is computed ahead. I will write into it, but this is not even written. Okay. Now, the worry is, if suppose I allow this writing to happen, after that this instruction anyway will be completed because it has to be completed in the sequence. They are all in basic block. So it will be completed later in time and then this value will be written. Now, some instruction which depends on this R1 is not getting this value which it is supposed to, but it will get the previous value which was not even expected to be available here because this instruction has come before this R1. So I cannot write before this write has happened. I need to, in other word, write after this write. So this problem will happen again only in dynamic execution because in a normal pipeline, this instruction will be completed and this writing of this value would have been completed. Then only this is going to write. So in the normal pipeline, I will not have this problem. So when you execute instructions dynamically, you have to take care of these two, which were not present there. Okay, that's all I wanted to say. Implementation of scoreboarding needs to take care that none of these data hazards, I don't want any of this data hazard to happen. They are likely to happen, but I should prevent it, okay, from affecting my correctness of the execution. Another goal I have, I need to have a maximum, one execution rate. That means one instruction coming out every clock cycle. So typically whatever we wanted to do in pipeline, I want to do this here also. With a lot of hardware here, I want to have this possible. In that case, what I should do, I should put maximum number of instructions in the execution stage so that all the functional units are executing in parallel without losing any cycles. Now, what is the architecture? This is very simple. I'm showing. A centralized hardware is controlling all these registers, which are registers are being here. This is physical registers. Okay. And then different functional units. There are two multiplier unit, one divider unit, one adder. These are all floating point. Okay. Remember, they're all floating point. And I have only one integer adder. Okay. In this particular example. Now, what am I using this for? I am using this integer unit for computing effective address. If I want to access some memory, I have some address and offset. I want to add it. That is an integer operation. Remember, memory addresses are all integers. They are not floating point. Memory addresses are never floating point values. They are all unique integer values, addresses. So I need to perform any arithmetic with the pointers. It is an integer operation. It's not a floating point operation. Please do never make a mistake that that's a floating point. Floating point is only for data which is related to applications like images, values, brightness, whatever. So they're all done by floating point functional units, which could be adder is separate. In a normal ALU, what you have, we do perform all these operations in single ALU. That is what was done in pipeline, integer operations. Whereas in floating point, multiplication is done by different hardware, division is done by separate hardware, and addition and subtraction. Please don't think that only it does addition, it does subtraction also. It is done in different hardware. Now, you are having so many instructions which are coming in with floating point, addition, division, all that. I can schedule them on this hardware in parallel. Why do I have a separate hardware for each? Because they are complex operations and it takes multiple cycles. I will explain to you how many cycles it is normally. It could be more or less. They take multiple cycles. So I cannot wait for one multiplication to complete before I start the addition. So we have put multiple hardware units so that they are all done in parallel, provided we take care of the data hazards. Okay. Now, what are the registers? Floating point units always operate on floating point registers. Remember that as well. And then integer unit works on integer registers. In our examples here, I will show you as some R1, R2, which are integer registers. If I show you F1, F2, F3, they are all floating point registers. They are different. F1 and R1 are different. They are physically in two different places, accessed by two different functional units. So the floating point registers F1, F2, F whatever numbers are there, they are all accessed by these hardware. They don't access integer registers. Similarly, integer unit accesses only this. They don't access this. Okay, remember that. Okay, so far so good. I am not going to explain anything more. Scoreboard is some hardware unit which takes care of the data hazards. Before I issue the instructions into this unit, I have to make sure that the operands are free of hazards. Now, I am going into the details of execution, implementation of the scoreboarding. Let me explain this a little bit. This I have explained. Pre-decoding happens here, and then normal decoding of instructions, like what are the operands, which are the registers the operands are coming from. It is understood by the processor here. Once it is done, now it is not sent to the execution unit directly. Execution unit is here. Okay. I said FUs. That means there are multiple execution units in the system. Remember that. Okay. There is not only one. In pipeline, there was only one ALU I showed you. Here, multiple execution units. That means what? Instructions come in as a single pipe, and then they go into these functional units from here. It is like a junction, 5 road junction or 6 road junction, where only traffic is coming in from one road, and then they all go into different paths. Then once they all take a different path, they get executed in a out of sequence, out of order. And each of those functional units take different amount of time. Division takes much more, and then multiplication takes little lower than division, and addition and subtraction much less. I'm talking about floating point division, multiplication, addition. So they take different time. That means what? Those instructions will be completing their execution out of order and at different point in time. When they complete the execution, the results are available now. They need to be written back into registers. That has to be very carefully done. Okay. Now, let me tell you what is handled where. The data hazards. You know that there are 3 data hazards available, possible, not available, possible. Now, what is write after write? If suppose 2 instructions are there, they both of them are writing into the same register, it is called write after write. Okay. Now, when will this problem happen? Writing is happening in this stage, correct? Actually, the wow, or I'll call it as write after write, really happens during this stage. You need to handle it there. That means, suppose I have started off multiple instructions, they are completing it in different time. Now, when I am writing the results, only after completion I will write the results. Okay, sorry, here I will write the results only after they complete. I need to make sure that which came first, which is next, that order I should know, so that I write them in the order in which they came in. In that case, then it will be taken care of. Now, in this implementation, scoreboarding, there is no facility for me to know after the instructions are executed and completed in this stage, I don't know which came first, which came next. And I cannot exactly predict how many cycles that instruction would have taken in the execute stage. It depends on the data. Sometimes the floating point multiplication, if it has to multiply a 0 value, it doesn't take so much time. It knows that 0 into something is 0. It just finds out in one cycle. But if it has to multiply 2 different floating point values, 2.5 into 5.6, it takes more time. It is actually dependent on the value in the register. So this stage, I cannot know if an instruction is coming out, okay, oh, this is a division instruction. It would have taken 10 cycles. So it would have started off 10 cycles before. All that I cannot assume because it depends on the data. Sometimes it may complete in 5 cycles, or it may take more cycles. So I cannot guarantee this wow unless I have some other hardware to take care. I don't have that in scoreboarding. So what is the best thing? Do not allow instructions which might land into this data hazard. Do not issue at all. Do not even make them run. Do you remember right now people are saying that if you are COVID positive, not you, someone else is COVID positive, they won't be allowed to board the flight. Why? They don't want to bother about after the flight lands, how many people got infected because of this one patient, and then how to isolate them, how to take action. It is too much to do after the damage has been done. So don't allow them. Don't maybe allow them to enter the flight. So same thing is here. If 2 set of instructions are there, one after the other, and they are likely to cause a wow problem, because we are not guaranteeing when this instruction will be executed, when it will be completed. We don't know. If you allow these 2 instructions to enter the execution stage, this may complete before. Once it completes before, I will not know whether this instruction was the first one to come in or the other instruction. Both may be in the execute stage. I will not know the order at the other end. So I should prevent it even allowing them to enter the execute stage. So remember one thing, because I cannot find out what is the order in which the instructions came in. I don't have the support in the hardware. This particular scoreboarding technique does not allow a wow instruction, an instruction which can cause a write after write hazard is not even allowed to enter the pipeline. Now, what do I mean by that? Suppose I have two instructions which are writing into the same destination register. I will allow only this to enter. I will hold this. I will hold it. I won't even allow it to enter the issue stage. Then what happens? It will not be even, only one instruction will be in the execution stage. Once it is completed, then I know, okay, this instruction is completed, the result has been written into it, then I can safely allow the next instruction to enter the issue stage. So if I prevent it from entering, like what I gave you an example, it is avoided at the later part. So that's what is shown here. Wow data hazard is handled by this issue stage. It is doesn't issue them if those instructions are likely to cause a wow problem. Please remember, it is not guaranteed. Suppose this instruction is also writing it and this instruction also writing it. Maybe this will complete first and then this next. Then it's no problem. There is no issue. But we don't know. We still don't know how long it will take for execution. So we don't want to take a chance. Okay. Similar to what I gave you example of COVID. Now come to the read after write. What is read after write? I have explained already. I need the operand to be read before somebody else is going to write into it. Who is going to write? Somebody in the next stage is going to write into the register, which is going to be read as an operand by the previous instruction. Now, how do I handle it? Oh, so I'm sorry, I'm totally mixing up this. Sorry, let me start again. Read after write. What does it mean? Let me explain this. I have not explained it today, so let me explain. There are two instructions. This instruction is writing into this register R1. Okay, some R1. And the next instruction is going to read the operand R1. Sequence you have to remember. This is R1, which is giving the result, and then the next instruction is going to read the operand. This is called, this read should happen after this write is over. This is called read after write. Now, you can imagine in a pipeline how we did it. If an instruction is getting executed, it was supposed to write the result and it was not available in the destination register, but it was available in the pipeline register. We passed it on through the forwarding register. You remember that. We handled raw, which happens in pipeline register using the forwarding logic. In scoreboarding, we don't have a forwarding logic. Okay. Halfway through result is available, I can send it to another instruction which is waiting for that instruction. I cannot do. Forwarding is not there. So what is the best thing to do? The order is like this. This instruction is coming next and it wants an operand which is to be written by the previous instruction. It may be in the execution stage. So I should hold on to this. I will not read the operand. Okay, I am holding it on RO stage, reading operand. I will not read the operand until this writing is done, which would have happened in the write back stage of this instruction. So it is handled by this stage. Now let me explain what are these stages. I decode stage is split into two. One is issuing and read operand. RO is read operand, not read only. It's read operands. So I will explain to you what all how it is done in the sequence. First, we issue instructions based on the hardware blocks that are available, which are not occupied. Then we read the operands. Once all the operands are read, it is going to be executed. Now, one more thing you remember, I will explain it in the subsequent slides. When you are reading the operand, there are normally two operands will be there. This read operand will wait till both the operands are ready. It will not say, okay, one is ready, I will read it. And then when this is ready, I will read it. No. it will go to execute stage only when both the operands are ready. If it is not available, both are not available, one is waiting for some other instruction to complete, then this instruction will wait. It will not read the other operand also. Remember, it will not read the other operand also if one operand is not ready. Let me explain. Suppose in a check-in, if you are going to a airline check-in, you are taking a ticket with a one PNR number. Two passengers are there, your friend and you. You are checking into the airport. Now the airline staff will not allow you to check in because this same PNR number, both passengers are there in the same ticket with the same ticket. He will say that please wait till the other passenger also comes. Suppose he is on the way. You cannot say I want to go in, you wait for the other person. When he comes, you allow. No. You have booked it together. There is one PNR number and we will wait for both. Otherwise, you cancel this fellow's ticket and then you go in. They insist that both of you should check in together because it's single ticket. Similarly, this is a single instruction. Two operands are needed. One is ready, that means you cannot just carry on. You need both to complete the operation. So there is no point in just allowing an instruction to go with one operand. So this will wait till both the operands are ready. I hope this example and that suits you. Okay, raw is handled here. Now what about var? Write after read. So this I explained to you. In write back stage, some instruction is executing and it has to write the result into the destination register. It is in write back stage. This instruction started executing first before this. Now the same register is supposed to be, suppose it is there in the read operand and it is not in read because it is waiting for one more operand to come. Suppose this is one operand which is still waiting from somewhere. So it is not reading this operand also. Though it is ready, it is not reading it. Now, problem is this instruction has to read the operand for it to write the result. R1 is ready now, but this guy is not reading it because it has to read the operand together. Now the other operand is expected from somewhere. That means this instruction is not yet completed. It has to write into that register. Suppose this is R0, okay, and R0 is written by this instruction and which is not yet over. That means R0 is not ready, R1 is ready, but the condition is both R0 and R1 should be read together for this instruction to complete the reading of operand. Now what happens? I cannot read R1. This instruction cannot read R1 because it is waiting for R0. Now because this cannot read R1, this guy cannot write into R1. Though it started executing first, completed now, it is ready to write the result, but it cannot write. So this is called, this write has to happen after this read, right after read. So what happens is during the write back stage, the instruction writing into this destination is stalled, waiting for the previous instruction to read. This operate. How it is done, don't bother. I am saying it is done and it is taken care of. Take it from my, believe me and trust me. So now let us see. All are handled. Wow is handled by not allowing the instruction to come in. Raw is handled in the read operand stage, and write after read is taken care of during the write back stage. So all data hazards are taken care of. So I am ready to go ahead now to show you the example. So issue stage. This is issue. IF and decode are done. Okay. Instructions are stalled if it is likely to cause a wow. Dependency. Dependency. Okay. Spelling mistake. With the instruction under execution in. Okay. Now dependency with whom? Dependency with whom? This can be because of some instruction which is here or something is here, which is prior instruction. Okay. There are so many instructions. Right after write will come when one instruction is supposed to write here and another instruction is supposed to write here. And this is already in either in RO stage or it is in execute stage. So I cannot issue this because of previous instruction could be in one of these two stages. Okay. So that is where the verb is handled. Okay. And then one more thing you remember, issuing is happening in order. That means instructions are coming in some sequence and issuing is happening in order. Execution is happening out of order. And write back is again making sure that it is done in order. I explained it multiple times previously. Maximum only one instruction is issued per cycle. Again, since I am issuing instruction in order, I'm saying it is going to be in order. I am here making sure that only one instruction enters into issue stage every cycle. I'm maintaining a sequence. Read operands. Waits for the operands to become available. Wait for both the operands to become available to read both operands. Okay, it has to read both operands together. It is not one after the other, or it cannot read one in this cycle, next in another cycle. This handles raw hazard. I explained it already. Execution, all the operands are available, then I can go into execution. If both operands are available and I have read it, I have crossed this stage, now it is going to be executing. Executing in one of the functional units. After, whenever it completes, it will come into write back stage. Okay. It takes multiple cycles and it may take different cycles. Now, out of order execution happens. Execution can be out of order because let me tell you, it was in order so far and then suddenly how it becomes out of order. Because availability of operands is not in your control. Once some instructions come in, wait in this stage, suppose multiple instructions are waiting in this stage, maybe operands of this instruction is available now. It may go into execution first. And then this instruction operands are available, it goes into execution next. The order is different now. Then this may be available, then it goes. So issuing is in order, but execution may start based on the availability of operands, and availability of operands depend on what? Availability of operands depends on the execution completion of previous instruction. Some instructions are getting executed and they are completing it, and in order, which order they complete is not in your control. So operands available is also not in your control. So once you issue it in order here, doesn't mean that the execution also will start in order. They are all waiting here for operands. Whenever operands are ready, it will go. Okay. So they are not dependent. Write back is again back into action. So writing of the results of out of order execution, whatever was executed out of order, okay, they are stalled for war and it is done in order. Write back is happening in order. So it makes sure that you put the results as per the sequence. So this is done, explained. If you don't understand fully and there are some doubts, don't worry, hold on. I'm going to explain some simulation, you will understand it. So the same thing I'm explaining here. Issue is happening in order. Now, how do you issue it? You take care of the structural hazard. This we have already spoken about structural hazard. You will not issue an instruction if there is no unit available for it. Okay, that is called resource not available. That is called resource hazard, which is also taken care during the issue, and this is also taken care during the issue. And read operands takes care of raw hazard, and you are checking for a war hazard in the right result. So everything is handled. We are now ready to execute the instructions. Now, let me explain what are the concepts. Every instruction goes through scoreboard. Okay. Scoreboard is a hardware module in the processor which maintains the information on data dependencies in the execution, instructions in execution, and controls the order of their execution. Okay. Based on the dependency, it controls, not out of order execution, which is happening. Because of the number of cycles, it may be different. That is not it control. It controls the execution of instruction. That means giving it to the functional unit, it controls based on the availability of operands. Scoreboard analyzes data dependencies of instruction. It analyzes it, it knows, and it decides when an instruction can execute. That means when operands are available, it will execute. Otherwise, it will wait. Scoreboard also, I'm saying scoreboard is some hardware, okay? Don't worry. Also controls when a functional unit can write its results. Now, Functional unit completes it. After that, it has to write the result in write back. It controls that also because it has to take care of the var hazard right after read. So it has to control it. Otherwise, individual units don't know. The scoreboard is a centralized controller which takes care of all of them. So it maintains the sequential consistency of the program, original order. So it avoids var hazard. So one more thing I told you, it doesn't have a forwarding logic in it. So it has to wait for the write back to complete before any instruction which is waiting for reading the operand starts off. It has to wait till it is written. There is no forwarding logic similar to pipeline. Now, it has multiple instruction in execution phase. Okay, this you should remember. Multiple instructions can be in execution on different FUs. So it is added two units, two stages. It has added, sorry, issue and RO. I'm explaining it now with the slide which I have already told you in my explanation. So instructions are issued and operands are read. So it's split into two. In our ID stage, in our pipeline, it was done in the same cycle, in the same CPU cycle, in the same stage. Decoding is all done and reading operand was also done. Now you see decoding is different, issuing of instruction to the functional unit is different, and reading the operand is different. So they are all split into multiple things. Decode is separate, one small job which is done. In fact, pre-decoding is also done. So wow hazard, right after write, it must detect. I told you this. Okay. Issue stage itself, you should detect and stop issuing it. An example I have given you. Both of them are writing into it. So that means what? If I am issuing this, I should not issue it here unless this is completed. So that is what is called wow hazard. So raw hazard, I already told you. Out of order execution, I explained to you that it should wait till the operands are read for writing. I hope all of them are clear. So I am going to a little more details. So out of order execution divides ID stage into issue stage and read operand stage. And one example I will show you. Suppose, okay, this you understand it. Div D, add D, D means double, subtract. Who is doing this operation? Div D is done by a divider, floating point divider unit. This is adder unit, floating point adder unit. Don't confuse it with integer adder. And then subtract is also done. It's a double floating point value. It is done by the adder unit. These are all the operands, floating point registers. Now, what is happening? This you understand what is this? It is writing this result into F0, which is recorded as an operand here. That means what? Read after write. This is RAW. Where is it handled? In the read operand stage of this instruction. That means this instruction cannot read the operand until this is completed. Okay. Remember one thing, you don't wait for issuing this instruction just because this is waiting. Okay. In a normal pipeline, if this is waiting, this will not even be considered for execution. In dynamic execution, that's one major difference. It will be considered for execution, provided it has all the information it needs. Now, what are the things it needs? Divider is going on. Division takes more cycles. So until division is done, this result is not going to be available. You cannot just override this. You need to wait for the division to complete. So this instruction, whatever you do, cannot proceed until this value is ready. And you cannot make it fast. Food has to be cooked. It will take some time. So add cannot proceed. Even if unit is available, adder unit is available, I cannot schedule it on that because it needs operand, which is not even ready now. It is getting ready. Now I don't have to wait because add is waiting. I don't have to wait for issuing this instruction. That is what is called dynamic execution. The hardware goes to the next instruction and sees, can I issue this instruction? I cannot issue it, no problem. Let me check whether can I issue it. It is taking from F12 and F13. Assume they are not being calculated now, it is available. That means the values are final. There is nothing prevents me from starting the execution of this instruction before even this fellow starts. Okay, before even this guy starts. So what do the hardware do? What does the hardware do? It sees whether I have a hardware now to execute this instruction, which is an adder, floating point adder, which is available because this is not even scheduled now. So I can schedule this instruction ahead of the previous instruction, and I can provide this operands, and it will complete. It will even complete the execution even before this fellow starts. Okay. So this is what is called dynamic execution, out of order execution. I am executing it out of order, but I am issuing it in order. That means what? I issue this. I have this operand. I read issue is done first, and then RO is done. Then execution starts, right? So I issue this instruction. I read the operand. I start executing. Next, I issue the add D. I issue it, but I can't start. I can't come into the RO stage. I cannot complete the RO stage. I can issue it because adder is there, but I cannot start the operation. I cannot start it because this is not ready. Now what I do, I consider this instruction. I issue it because right now the unit is free. The adder unit is free. There is only one FP adder unit. If you remember, there are two multiplier unit, one divider unit, and one FP adder unit. So since this add instruction is not using the FP adder unit, it is free now. So I can schedule it. I can issue it, and the operands are available. So it will proceed further and start executing even before this instruction starts. Okay, this, if you understand now, it will be helpful for you to understand the simulation that I am going to show you. So there are two stages. I am stopping it. Issue stage is stopped based on the availability of the hardware and the warp hazard, two things. And read operands is prevented by raw hazard. If both are cleared, instruction starts executing. Okay. Now implementation. We are coming into the implementation of that. There are 4 stages, as I told you. Okay. This we are doing it before, so I am not even considering it. Now I'm going to show you something interesting. You have to be really careful now. I told you multiple functional units, right? I have to maintain a status of for each of them. I have to maintain some status in the hardware so that I know whether this is busy or not. And if it is busy, that means what? Some instruction is getting executed there. Once I know some instruction is getting executed, now I should know where it is supposed to write the result into, where it has taken the values from. So some information I need to maintain per functional unit. Okay, because after issuing, the issuing of instruction is done based on the availability of functional unit. And so an instruction is assigned. Suppose if I know that it is an integer add, I will give it. If it is an integer multiplier, I give that instruction to this unit. If it is a integer operation, I give it. So I issue and I assign the instruction that, oh, this is a functional unit, can handle it. Provided the operands are available, you take it and execute it. So I assign it, I issue it to the hardware. So after issuing only, I worry about operands. That means I should know what are the registers which are feeding the operands to this functional unit for the instruction, particular instruction to execute. So I need to know the status. First, I need to see whether it is busy or not. I have a Boolean flag to indicate whether it is busy or not. If there is an instruction in the functional unit which is getting executed, the unit is busy. Otherwise, it is not. Now, another thing, operation, because adder means I don't know whether this functional unit is supposed to do a adding operation or subtract operation. So I need to have one number of bits, some number of bits to say what is the operation to be performed. And example is div D being executed in div unit. Okay, divide operation is done by div unit. Multiply operation by some multiplier multi-1 unit. There are multi-2 and multi-1, so multi-1. subtract operation is to be executed by FP add unit. Now I am saying being executed. Okay, this div D is already in execution because these two operands are ready. Okay, and then this is also being executed. In my case, 12 and 13 are ready, suppose, and it is writing into F2. Okay, no problem. Multiplier unit can do it. And can I allow this addition to happen? Operand F2 has to come from this. I am saying it is being executed. That means the F2 is not ready. This operand is not ready. So sub B cannot get into execution until F2 is ready. This is called read after write. So if I have to maintain a status for this instruction, which is being executed by a FP add unit, I have to say this busy is currently, it is not busy. Okay. Adder unit is not busy. Assume that there are no instructions which are performing addition. Adder unit is not busy. One instruction is assigned to it, issued to it, but it cannot start executing because operand is not ready. So what is the operand to be performed? If suppose when it is to be executed, when it is likely to be executed, it is supposed to do subtract operation because sub is the operation. Okay. So now I am having another field for, I am telling you that it is maintained for every FU functional unit. I am talking about one subtract instruction which is assigned to a functional unit, which is an adder, floating point adder. And I am showing you what are the values it is supposed to have. Operation, it should have subtract. What should it have an I, Fi? What is Fi? Is a destination register. Suppose when this FP add completes the execution of this instruction, where is it supposed to give the result, put the result into? It is supposed to put into F1. So Fi is the destination register. Fi is a generic name given. So Fi, Fj, Fk. You have to remember this nomenclature. Fi, Fj, Fk. So Fi is the register where the result supposed to go. That is F1 here. If I have another instruction, add D, F5, F7, F8, these values will be different. Addition operation will be addition, and this instruction Fi will be this. So it's a variable assigned a value. Okay, you can assume like that. Fi is a variable. A functional unit maintains some variable, set of variables. Based on the instruction being executed on that functional unit, it is getting some different values. In this case, Fi will be F1, Fj will be F2, Fk will be F3, two operands. Okay. I hope this is clear. Fj and Fk are the source operands. Where is it coming from? Which registers? And Qj and Qk, what are they? They are the functional units producing the operand. Qk is the functional unit is producing the operand Fk, provided Fk is not ready. You are waiting for the result to come from some other functional unit. In that case, this value is a functional unit. Let me explain in this case. Can you say what is Qj, Qk for this instruction? See here, F3 is what? F3 is coming from where? It is supposed to come from divider. So Qk, Fk is coming from Qk, which is nothing but a divider. So I am giving Qj first. Let me tell you about Fj. Fj is what? Nothing but F2. F2 is coming from multiplier 1 unit. It is still not at over. Okay. Both the operands are not ready. Both are coming from different function units. Then only this guy can read the operand and proceed further. Now I am holding that information in these variables. So Qj is multi 1 and Qk is divider unit. If you understand this, the rest of the simulation will become easier. Let me explain once again. When the instructions are getting issued, they are issued based on the availability of hardware. There is one divider available, there is one multiplier available, there is one adder available, floating point adder. So it is issued. Now they have come to read only operation, reading operand stage, RO stage. Div D has both the operands started executing. Mult D has both the operands started executing. So they are in EX stage. So that is the state we are in. Okay. Both instructions are in execution, but not completed. That means this is not ready. This is also not ready. It is getting executed now, multiple cycles. Now I have sub D is in the issue stage because I have the adder which can perform this operation. So I have put it in issue stage. Now I am maintaining the information about whichever instructions are there in the issue stage and for which functional unit. It is for the FP adder unit. So this unit has an instruction which is supposed to perform an subtract operation by FP add unit. It has to write the destination value. Once it computes value, it has to write into Fi, which is nothing but F1. And it has to read the operand from Fj and Fk, which is nothing but F2 and F3. And they are coming from Qj and Qk, which are in execution now. Qj is getting executed by multi one unit, and Qk is the functional unit, which is div unit, which is computing it. So unless these units give me the results, I cannot proceed further. So this information, this is how it is making sure that operands are available before they are read. So what is the hazard? Read after write. Read these operands after these writes are done. So raw is handled, I told you, in this stage because it is having this information. Okay, how it is done, I am showing you. So it is going to wait for those operands to be ready. So now what is this RJ, RK? They are flags. This you will understand it maybe when I explain the simulation. Now it is little difficult. Let me explain it. Those who can follow, try to, otherwise don't lose heart. These are the flags indicating whether Fj, Fk are ready, whether these operands are ready or not, and not yet read. Okay, it is very confusing statement. Let me tell you. I told you in the read operand stage, an instruction has to proceed here only when both are ready. But in our case here, both are not ready, but it is not always true. Some may be ready. Okay. Suppose it was not F3. Okay. For a moment, you think it is F8. Okay. F8, I can put it. F3 is available. So then this unit, I don't have to maintain because it might have come from some other unit. Don't worry. This flag only indicates whether I am waiting for the unit or not. Okay, whether it is computed or not, the operand is already ready or not. Okay, that is made sure by using this flag. Don't confuse it with the integer register values R1, R2. I told you this is a variable per functional unit. So RJ, RK are the Boolean variables saying whether a variable, an operand, this operand Fj and Fk are available or not. So in this case, if suppose if it is F8, not F3, this F3 is available, then I will have this value RK as yes. Yes, I have it. I have the operand ready. Whereas for RJ, it is not ready. So I will have no. And no, if I say I have to come and see where is it coming from, then it is coming from multiplier. Then I will know. So I have to see whether it is no or yes. If it is no, I will come and look at the unit which is supposed to give it. See, the result might have come from this unit, but it would have completed. Still, it may be saying it has come from div unit, but if it is no, yes means that is available. The value is available, but it came from div unit. In that case, I can assume safely that the value is ready for me to read. So let me ask another question. When will this instruction be scheduled? When will it be executed? Only when both the operands are ready to read. That means this flag should say, is it waiting for something? Not at read. Okay. If it is yes, that means indicating is rest. Yes. If it is yes, it means it is ready. Okay. So hold on. And if it is not yes, that means it is red already. Okay, not at red also, it is a yes. Okay, so no means it is already red. Yes, if operands are ready and not at red. No means if it is not ready. Okay, it is little confusing. I will explain to you with the one execution unit. Okay, one simulation I will use it. And then finally, we are not at over. Only one more thing is there. I told you about write back, right? We have now spoken about write back. So instruction may be completed out of sequence. When you write back, I have to wait till there are no var differentials, right? I should wait till read is done by for writing. So how do I do it? I have a unit. I have, for every register I maintain, where is the destination coming from? The values are coming from. F3 is coming from a divider. F3 is getting the new value from divider. F2 is getting it from multi1. I have to differentiate between multiplier 1 or 2. And sub D is coming, which is writing into F1, it is likely to come from FP add. So I am maintaining which functional unit is going to give me the result of these registers. So just don't worry whether you don't understand it fully. If I show you an example, you will be able to follow. Okay. So let us see the example now. Okay. Because you are fresh now, I don't want to give a break. Please hold on. We'll complete it and take a break so that you will have a whatever I told you, you will be able to make sense. Okay. Now, these are the instructions I want to execute. They are all in basic block. Okay. All of them can be run in parallel provided there are no data dependencies. F5, Fj, Fk. These are the things which I explained to you. Now, this is a load instruction which is computing the address with 4 plus some R2 value and then loading the value from the memory into F6. This similarly loading into F2. Okay. And multiplier, subtract operation and division operation and add operation. They're all floating point operations. I don't have to say anything. I am going to refer them as I1, I2, I3, I4 instructions. Okay. Now, cycles. I am going to assume loading is taking only one cycle in this case. Multiplier is taking 10 cycles. Subtract takes 2 cycles. Similarly, addition also takes 2 cycles. Division takes 40 cycles. Okay. So what are the cycles? If once the instructions after the operands are read and assigned to the functional units, they are all in these different cycles. They will take this many different cycles to complete. Okay. So hope you understand this portion. Now I showed you some 9 variables are shown here. Okay. Whether a unit is busy or not, if an operation is going on, what operation it is supposed to perform, it is per functional unit. Okay. So one row corresponds to one functional unit. Now we have integer functional unit, multiplier, 2 are there, floating point adder and divider. I am not saying FP, it is a FP only. Okay. I have each row for each functional units and values of these variables. I will fill in these values only when an instruction is in the functional unit or issued. It is issued and waiting for operand. I will fill it only then. Otherwise, I won't fill it. It will be free. So when it is entering here, any instruction is entering here, I will make an entry here. Okay. I will show you the simulation. And when operands are read, it is completed. I will go from here to execution. Once that many cycles are taken by those instructions, I will go to the right stage. So I will move the stages. This is like a pipeline stage of each instruction. Okay. You can see that each instruction is going through different stages of at each cycle. Okay. And during this execute cycle, they will take this many things. Once the instruction lands into this executable stage, you can divide this into stages. Okay. So it's a pipeline, but different instructions will be there in each of the stages. Okay. and they all can move in parallel. Remember, these functional units can perform the job in parallel. What I mean by that, suppose multiplier is doing 10 cycles here. This instruction, suppose it comes here and takes 10 cycles here. At the same time, the divider also can perform the operation. They can happen in parallel because there are different functional units can execute in parallel. So you have to keep that in mind. It's actually very, very involved, very interesting, at the same time, very challenging. If you understand this completely, I can tell you, you can ramp up, study anything in the later stages on any architecture, because this is very, very interesting thing to understand. Okay. So let me start with this one. I have not explained to you. Every register that I have in the system, I will say which functional unit is giving it. Suppose F6 is supposed to come from loader unit, I will say loader. I will write an integer unit because integer unit only is performing the loading operation. So let me start off now. First cycle. I told you issue is going to happen in order. Issuing of instruction is going to happen in order, and I will issue only one instruction at a time in a cycle. So first cycle, I am going to issue this load instruction, and every cycle will move from one to the other. It is not going to just go through it suddenly. It will take, every instruction will take one cycle to move through. Now I1 is issued, I2 cannot be issued. Now why I cannot issue I2? Because I can issue only one instruction at a time, and in the next cycle also I will show you I cannot issue this during the next cycle, because loading operation involves some integer arithmetic which is to be done by this one single unit I have. While this instruction is issued and it is to be done, I cannot have this instruction in the executable stage. Okay, so I have to hold it. So let me tell you, second cycle. Now you may wonder why I am not doing anything here. I told you I will go in this order. Issue is in order. So since I am not able to issue this I2 now because of the resource hazard, I cannot go further. I can't even look at the dependency and all that, because I have to make sure that instructions are entering into the issue stage in order. Remember, execution only is out of order. Issue is in order. So I cannot just keep going down and then, hey, this is free, shall we put it? No, I have to issue it in order. I am not able to issue this instruction into this place because I don't even have a resource. I don't even have an integer performing this operation. So I can't issue. Issuing is done by based on resource availability. Resource means the particular unit should be available to me. I know very well. I have put one instruction now. Previously, I1, I2 cannot even issue now because I don't have an integer unit to perform. There is no point in issuing it, and I need to maintain it in order. That is my goal, because that will take care of so many other things that I need to handle. So I will go it in order, so I don't issue it. Now what happens? It comes to the read operand stage after the issue stage. Can it read the operand? Or to assume that it is available. It is not, I am not showing you any other instruction. That means you can assume that there are no dependencies prior to this. So I can read it. When will I read it? During this cycle, I will read the operand R2. 4 has come from the instruction itself, is an offset, which will have to be added by this unit. Okay. So now let me show you the different values which are filled in now. Is it busy now? Yes, I have the instruction now issued, so I call it as busy. Load operation has to be done, whether it is load or store, I don't know. So load operation now. Where is the FI coming from? FI is, where it is supposed to write FI. It is F6, it's a destination register. And I don't show the constant here, I will show only the registers. If it is coming from an offset, I don't show it. FK is coming from R2, I show it here. And not at red. If it is not at red, I will say no, I said, okay. And is it available and not at read. And not at read. Not at read means, has it been read? No. So it is saying no because this operand is not at read. R2 is not at read. It is in the read operation stage. After this only it will be read. So it is no. It is not at read. And here I have to maintain which functional unit is going to give me the value. F6 is going to come from this integer unit. When it completes the execution in the write back stage, it will come from integer unit. So I say integer here because F6 is a destination register. So this is what is done. Now can you guess what will happen? Next stage. In the next cycle, third cycle, it is now ready to execute. Correct? Because these operands are ready, available. I can perform the addition and then put the memory. See what all is happening in the execute stage. It has to compute the address, effective address, put it to the memory, get the value. Once the value is ready in the CPU, read from the memory, it will go to write back stage. Till then, it is in the execute stage. I am assuming it takes only one cycle for execution. So, third cycle, I1 loads memory contents. I1 loads memory content in, but F6 is not yet updated. Remember, only in the write back stage, the F6 is updated. So I have not yet written. Now, is the integer unit free now? No. Till the write back happens, I don't free the integer unit. Okay. It is because integer unit is responsible because it is holding the value. It cannot start the next operation until the previous result is written into it. So that is because there is no forwarding logic. So it cannot take the next instruction. Okay. So I cannot issue the next instruction until the write back happens. So then only the integer unit will be free to take next instruction. Now next cycle, you can guess it right. Now it is read. Now what is going to happen in the next cycle? In the next cycle, integer is operation is done. You can see that F6 is already written, so I have removed this value. Write back has happened. Okay. Now what do you think will be issued? If you are guessing it correct, I can issue LD next LD now because integer unit is free. Okay. But then it is like this, you should have say busy yes is there. No, it is a simulation I am doing. Now next one I will say no and then I will issue it. Then immediately it will become yes. So it is like transition stage. Okay. Till it is written, it is not free, but it will happen during the cycle, so don't get confused. At the end of write back stage, it is free. So at the beginning of issue stage, this instruction can come in. Okay. So it will continue to be yes now. Don't get confused. Now I am issuing only one instruction in a cycle. So I cannot take this instruction next. So I am issuing only this. Okay. So once I issue this instruction, this integer unit values will change based on what is in the going to be executed. It is now going to execute this. So I update this value. It is going to write the result into F2. So I write this value. This is also load operation. So I say load. Is RK available? Yes. R3 is free. It's available. It's not coming from different functional unit. And then F2 is going to be written by integer unit. So this is available. Okay. Now, I will, what do I do? Okay, I am already late. Let me pause. Okay. This simulation, I will again start from the beginning and give you a summary. Even if you have not understood anything, this simulation you can understand now. If you listen now, next 30 minutes. So we have a set of instructions which we want to execute. And we have a hardware scoreboard, which is handling the scheduling of those instructions. We have these multiple functional units, which are ready to execute instructions, provided the instructions which are coming in have their operands ready, both the operands ready. Then it will start executing it, giving the result, and it will be written back into the register set. One thing you remember, these instructions can be started off out of sequence, out of order. And since we are starting them out of sequence, out of order, they will complete out of order. Once the instructions complete execution, only execution stage I'm saying, not when I say instruction is completed, it means, suppose if I take this example, if I say instruction is completed, that means it has added it in this case, and then result is put into the F6. That is what is called instruction completion. Resume recording. So I'll continue from where I left. So these functional units are ready to operate provided they are given instructions with along with the operands. So we are talking about how it is scheduled. Initially, I told you issue is in order. That means instructions are issued. It will come to this stage. Then they will read the operands. Then it will get executed. Then the result will be written. Now, before issuing, one thing has to be taken care of. First thing is the unit should be available. You cannot have two floating point addition instruction to be scheduled or issued to the same adder. Only one can be given. Until it completes, you cannot give it to the same functional unit. So that is one thing. Second is I am issuing the instruction one after the other so that I maintain the order in order. Second, and then now let us start. So we have these different cycles for each instruction. It takes multiple cycles for execution. And we are maintaining the output functional unit. The functional unit which is going to give this value, going to write into this value register, is maintained here. And we have 9 variables maintained per functional unit. Okay, as we go, we'll understand what they mean. So first cycle, this is issued. And second cycle, I can issue the next instruction provided I have the functional unit. That means there is no resource hazard. In this case, sorry, I am not showing my own window here. How do I get it? Okay, sorry, I have to stop in between. Okay, let me proceed further. So come back again. Now, so this instruction I cannot issue now in the second cycle, though I could have done it if there was a unit available. So it has to be performed by this unit, so I cannot issue it. So it is going ahead, operand is read here, execution is done, memory read is done, and the result is written. This is where we stop. So let me start from there. Now, on the fifth cycle, this instruction is coming in. That means same unit is used, integer unit, whereas F2 is the result, where it is supposed to be written into. R3 is one of the parameters. This is Fk. And is it available? Yes. So now you see this instruction, while it is moving to the next stage, a new instruction is getting added. Because I can do it now, because multiplier unit is free anyway, right? I don't know whether operands are ready, but unit is free. So I am scheduling it, issuing it. So during a same cycle, it can happen. So, but only one instruction is coming in. I can't issue multiple instructions because I want to maintain order. So in a cycle, I issue one instruction. So multiplier unit is getting on instruction. Whereas this will go forward to the next stage. Like a pipeline, it moves in. What will it do? It will read the operand. Okay. What are the operands? R3, and this is available, so it is supposed to read it. Now, can you guess what will happen in the next cycle? Before I show, you should be able to estimate it, or at least see that this will move for sure. Now, will this come here? And then another new instruction can come here or not? These are the two questions to be answered. This will come for sure in the next cycle, cycle 7. And a new instruction can be scheduled because I have a FP adder free. Whether the operands are not there or not, don't bother. It is free, so I can move. So I can schedule one instruction here, a new instruction, this sub D on, I will get an entry here. And this will move to the next one because available, operands are available, both are available. Now, will this multi come here? Okay. Whether can it get the operands if it moves? See, when it comes to any operand stage, read operand stage, that means it should be available. Remember, you cannot say come inside and then say the operand is not there. Okay, it is like this. When you come into the exam hall, you should be ready with all the pen, pencil, all that. You cannot come into the examination hall and then say, no, I have not brought my calculator, my pen, and that is not allowed. Similarly, if an instruction is coming into the operand stage, that means it is ready to read the operand. Remember, okay? Now think about it. Is it ready? F2 is yet to come from this instruction, which is not even complete, not even started. So actually it doesn't have F2. So if it comes here and tries to read the operand, what is it going to do? What is the hazard? It is going to read before even it is getting written, right? So it is supposed to do read after write. F2 should be read after F2 is written. RAW. Now, can it read F4? Of course, yes. But I told you an instruction will not read one operand at a time. It will have to read both operands and it should be ready. Now F4 is ready, but F2 is not. So I have to now think about it. Next stage. As I told you, it is not moving into the operand reading stage because it is not available. F2 is not available. When will it be available? When this is also done. Right now it is reading, loading. This instruction is executing. Please remember all this, what you see, each row is done in sequence and they are all in parallel. So it is being accessed. Memory is being accessed. It will be written into that in the next cycle. Then I can read the operand. Till then I cannot. Now I have issued this. That means I know that subtract unit is available. So I issued it. Now can you guess what will be the next instruction? Do. In the 8th cycle, what will happen? These are all the cycle numbers what I am showing. What is happening during the cycle? I hope you would have understood by now what the numbers are coming. These are all cycle numbers. So 8th cycle, what will happen? Div D will come into the issue stage. Why? Divider is available. It is not busy. Correct? So it can come in. But whether it will go to read operand stage or not, we will see. We will not worry about it now. Okay. Can it move here? Still not ready. F2 is not ready, so it cannot move. Can this guy move here? It wants F6. F6 is already written because the 4 is completed. So F6 is ready. Sorry. But again, this also depends on F2. It can read only after this write. So even this will not be able to move to this stage, and this also cannot move to this stage. Only this guy can move now because I said load is going to take only one cycle. Okay, all this you have to keep it in mind when you are doing it. My video is gone. No, I don't think you need it. Okay, so guys, 8, what will happen? This is what happens. This is completed in the sense the result is ready. It is yet to be written. It is going to be written in this cycle. And Down, if you see, we have created entries. I want you to analyze it. Very simple. This is F8, F6, F2 is same as F8, F6, F2. F10, F0, F6 is same as these three. Nothing great. Now, FP adder wants F2 now, F6 now, which is available now because the write back has happened. That's why I think I've shown it as yes. Whereas F0, F6, here I am saying no because F0 is not even started. F0 is not even started. Multi-D is still, where is the multi-D? It is here only, okay? It is not even started. So F0 is not yet ready. Because write back has happened, I am saying that this route two, during the write back, this flags changes will be, I may show it before because you should know that the next cycle it can be read. Because write back has happened, that means F2 and F6 are, during the cycle, F2 and F6 are written. F6 is already written, F2 is also written. So this has got both the operands ready now, okay, which is multiplier. This is the multiplier instruction. Both operands are ready now because F2 is written, F4 is already ready earlier itself. What about sub D for subtraction? Both are ready because F6 is already ready, F2 is also ready now. Now you can guess what will happen in this cycle. Two instructions are going to get into read operand stage. Both of them can move now because they see that in this cycle both are getting written. The results are available. F2 is written, that shows that these two are available. F4, F6 were available earlier itself. So when both operands are ready, the instruction will move to read operand stage. Okay. Now one more thing you have to think. Can this move? It is waiting for F0, which is coming here. So it cannot move. This cannot happen. Now, can I introduce another instruction? That's what every time you have to think. Every cycle I have to think, can everything move or can I add more? Now, if I have to move this instruction into the issue stage, I should have the adder ready, available. You see the F adder, FP adder, it is busy now. It is busy, yes. It is busy with what? Subtract operation, which is this instruction. It is still not ready. So, since adder unit is not available, I can't issue this. I can't put 9 here. This instruction is not even being issued at cycle 9. Okay, this you can understand. I want you to run through this video again, understand it yourself, okay? Because it takes time. I am going to ask some questions on this, maybe 10 marks or something. So I want you to clearly understand what is explained here. That's all. I'm not going to ask you the same question, but little different. I'll ask you to think about it in the exam. So now, ninth cycle, I am sure these fellows, both of them can get into this. Okay. So let us see. Explanation, I'm not going to read it. You read it later on. I am providing the explanation. I don't want to waste time on reading it. So 9, 9. Very good. Now what will happen in 10? What will happen in 10? Cycle 10. Cycle 10, both of them will come here because both operands are ready. So it will, during this time, it will read the values and it will come into this stage. That means what? Execution stage. Both multiplication and subtract operations are going to be started on two different functional units. Remember, two different functional units. Now, this guy cannot come because F0 is not at ready. F0 is not at ready. I cannot move it. Similarly, I cannot do anything here. So my progress is going to be seen only here. So what happened? Cycle 10 is not shown. 1 second. Let me explain what is happening. I think I made any mistake or what? 1 second. Okay. Somebody is writing it. I am not able to see that what you have written. 1 second. Okay. Yeah, I got it. Your point. Thanks for that. I'll show you. You are right. So I am not showing it here, 10th cycle, because I am showing the cycles only at the end of the operation. Okay. Till then I won't show you. Now you may wonder why cycle 10 is not shown. Because subtract operation is taking 2 cycles. I am showing it at the end of the cycle, execution done. Okay. It is only not the entry, execution done. So I don't show it the cycle 10 here. Similarly, I don't show anything here because it is going to take 10 cycles from 9. From 9, it is going to take 10 cycles. That means till 19, I am not going to show anything there. Okay, that's the reason. Okay, so thank you. So what I am going to do at cycle 11, it is completed. Now you may wonder what would have happened in 10. In the cycle 10, what was happening was both of them was getting executed. This was making some progress. This is also making some progress, but I can't add anything here. This guy cannot move anything, so I don't have to show anything. Okay, so there is nothing wrong in the execution in the what I'm showing you. So once I finish it at 11, the result is available, but not yet written into F8. And this subtract unit is not yet free. It's not yet free. Remember, the result is still there with that unit. It has to give it to the register, then only you can get. Now 12, you can easily guess what will happen. At 12, this guy will move. It will take only 1 cycle. Okay, writing will not take more than 1 cycle. Only execution takes a number of cycles. So 12 is easy to guess. It will come. What will happen? F8 will be written. Where is our friend F8? It was supposed to be written by subtract unit. It is written. I'm showing you at the end of those cycles, right? Result cycle. Now F8 is written. Now what will happen in third cycle? Now tell me what all is happening right now. Which are the units are busy? If I ask you, if I show you only this picture and then ask you, which are the functional units are busy? Only this guy is busy. What is it doing? It has started off at 9. Right now we are in 12, then 10, 11, 12. 3 cycles are over. It is halfway through. It is busy doing multiplication. What about other units? They are all saying it is busy, but they are not doing anything because they are all waiting for the operands to be ready. This guy is also completed it. Now it is waiting for the write back to happen. Okay. And it has happened just now. Subtract unit, this adder unit, subtract, the operation is done now. So you will see no when it is not at ready is no, because it is ready. The operands are ready and then it is even completed now. So what will happen now? Can you guess on 13 what will happen? This guy will make some more progress, but it won't be shown here. But there is going to be something introduced here. Why? This is done now. This is done. Adder is going to be free, which now can take a new instruction I6. So 13, I can introduce the new instruction now. So 13, it is introducing a new instruction. And then what will happen? Can it read the operands? Now 14, you have to worry about 14 now. In 14, can it go further? Still keep on remembering that this instruction is F0, which is waiting for this result, which is not yet ready. So it is going to be considered only when this is coming to 19, then after 19 cycles, after 10 cycles in the 19th cycle, and then 20th cycle, maybe this fellow will move. Till then, you don't have to worry. Now, can so you cannot proceed. Can it proceed? The question is, can it proceed? And cycle 14. What is F8? Where is it coming? It is already available. F8 is available. F2, of course, it is available. So none of this instruction is writing into F8 or F2. So it can comfortably move into next stage now. It has moved. Now it has read the operands during this cycle. How long will it take to complete? 2 cycles, because it is taking 2 cycles. So 15 will not be shown, 16 is shown. Now once 16, it has completed the execution. Now it has to write the result. When will it write? In 17 it will write. 1 second. Why is it not writing? Okay, did I make a mistake? Now I have explanation you have to see. I want to write it in 17, okay, really, but I'm not doing it. Why? Let me explain. Where is it writing? It is writing into F6. Result is supposed to be written into F6, but F6 is here, which has not been read by this instruction. See, this is the typical example of war hazard. Write after read. So this I am showing you a war hazard, which is handled by write back stage. So you may think that it has to write into it in 17th cycle, but it is not writing. Why? Because of war hazard. If it is supposed to write into F6, result is available with the unit. It is supposed to write into F6, but it knows F6 is not at read, because div-D will read both the operands together, and it is now waiting for F0 to be ready from this instruction. Remember, it is going one after the other. So F6 was ready earlier as far as this instruction is concerned, but it is not reading it because F0 is not ready. And F0 when will it be ready? When this instruction is completed. So when it writes the value, till F0 is completed and both the operands are read by this instruction, add cannot write the result. If it writes it, it is going to overwrite the value which is there currently. So it is holding. Write back does not happen. Write back of this unit will not happen. So it is not proceeding further. When will it proceed further? After this read operand is done. When will this read operand happen? After this is complete and this is complete. Now when will this be complete? In 19th cycle, because it started off at 9th cycle and it is going to take 10 cycles to complete. I can't wait. I can't proceed further. You have to wait. You cannot suddenly increase the reduce the time taken for the execution. 10 cycles it has to take. So 17 is skipped, nothing is happened. 19, things are now ready. Some light at the end of the tunnel now. We see that F0 is computed, but not at return. F0 is not at return. It will be written here only. So next cycle 20, F0 will be written. Okay. You cannot do it in the same cycle like what we did in pipeline. I write it in the first half cycle and you read it in the second half. No. Because it is not between two stages. It could be many instructions could be waiting. So I cannot make this read of this happen during the same cycle. So that another difference between a pipeline and this is write and read happening on the half cycle, which I showed you in the write back stage of the pipeline, is not happening in this. Okay. So write back is not happening. Write back is happening, but reading is not happening in the same cycle. Now you can guess what will happen in the cycle 21. Because this is done, that means F0 is written, multiply operation is completely done. So F0 is ready, F6 is also was ready long time back. Div-D can read both the operands together during the next cycle. Okay. So in 21, it reads both the operands and then starts off execution. In the next cycle, it will start off execution in the divider unit. Divider unit is doing it. Now, adder unit is still waiting because it has completed a job, but it has not completed this. It is not returned the result yet. So it cannot proceed further. So it is still busy waiting for this F6 to be written into. When can it write? When this hazard is removed. This hazard will be removed. The write after read hazard is now done. Reading is done now. Divd has read the F6. Now F6 is not having that var hazard. So in 22nd cycle, I can write it. I am ready now. It is free. There is no hazard. I can write it. If you see one interesting thing, this instruction which has come later than div, okay, in the execution sequence, this should have been completed and then this should have been completed. Now, one second, there is some question there which I am not able to see. Hold on. Don't write into chat window unless you have something to ask. I'm not saying don't write it at all, but write only when you have something. Please don't write some junk. Okay. Where was it? My flow is disturbed. Okay. 22nd cycle, the result is written and the adder unit is now free. Next cycle, it will be free. But we don't have any instruction to schedule. We are not showing anything. Now, what is next? The next is you have nothing to do other than waiting for divd to complete. Divd will complete after 40 cycles. It started off in 21 cycle. So you have to wait till cycle 61. If I show you till 61, you will all die, even I. So I am going to jump to 61, assuming 40 cycles elapsed. Okay. So 61 is result is ready, not at return. And in 62nd cycle, the result will be written. Now, all the units are free now. Nothing is expected from any functional unit. Everything is written. So this is how the execution happens. Okay. So you have to listen to this again if you want to understand it. Where is what hazard handled? How, in what sequence these things are written? Understand it. Because I will show you some state in the exam. I will fill in some values here, some cycles here, and then ask you in the next cycle, what is going to happen? You have to write the answer only in the next cycle, what is going to happen. Do not assume I am going to write the same instruction. Do not assume I am going to use the same registers. No use of mugging. Do not assume the cycles will be same. Maybe I will keep it same. I don't want to complicate too many things. I understand you have to think during the exam. So I am nice, not very. I want you to answer rather than I don't want you to answer. I want you to answer. So I will not change these values. I may change the order of these instructions. I may change some of these registers. And then I will maybe show you the values. I have not yet decided. I have to, actually, if I have to show you, I have to execute it through the sequence, which is very difficult for me. This simulation itself took a lot of time. If you are all now giving presentation slides, I see that you guys are doing. Try doing this. You know, there are lots of possible problems. I spent a lot of time in building this sequence. It's not easy. PowerPoint does not provide you all kind of facilities. I hope you appreciate and understand this. I am not going to spend more time. I have spent already more. So what are the limitations? Let me stop with the limitations and then I will show you something else next class. The amount of parallelism available among the instructions is limited because it operates only within basic block. I told you basic block only I have to consider. Instructions are not too many within basic blocks, because you normally have if condition, then you write only small code inside if, then you will put else, then you write small code. So what you write here is only is generator and assembly instruction. So basic block is not too many instruction unless you write so much in if. But in real life, it is not true. So you may not have too many instructions within the basic block for you to schedule using all the function units. So what I'm saying is you will not have sufficient instruction to parallelize. So you will not get such a benefit. Even if you have seen in this example, I have shown you instructions with all dependencies together, okay? Many dependencies. So you see that if you are very smart enough, you might have added these instructions and then see how many cycles it would have taken. I think I added it. It was 64 or something. Not 66. 66. Okay. So how much am I gaining? If you see, I took 62 to complete all of them. Did I gain anything out of all this business? No, I didn't gain much. I took 62 cycles to finish all this instruction. Whereas if all of them would have been executed in sequence, the execution itself takes so much cycle, 66 or something, if you add it correctly. Not 66, I'm sorry. I made a wrong correction. 56 plus all this what is coming before. So if you had to add all of them, it may be a little more. Okay, you are not their execution cycle is only the time taken for execution. I'm not talking about write back. I'm not talking about other cycles, and then even the decode stage and the IF stage. So if you add up all of them, I'm likely to get around 66. Okay, 56 will become 66. You can do that as a homework exercise. This is only execution time. So I have done it in 62 cycles. Even if I spent some time in these cycles, I still managed to do it in 62 cycles, but which is not very great for the amount of work we have done in the hardware and a lot of things. That is because there are so many dependencies between the instructions. So don't think that it is of no use. Okay, it is of use, but it is not giving you complete benefit because of this. So number of scoreboard entries window is not beyond a branch. So it is the problem. No forwarding is there. That's another problem. Number of FUs in processor limits the parallelism. If I have more integer unit, I might have started off loading parallelly. So it is limiting it. And then waiting for write back for the var delay is also, again, you have seen the delay because you are waiting for the result to be written for the previous instruction to complete. So these are all the issues. Okay. And you were waiting for issuing the instruction to avoid wow delay. So there are issues. I'm not saying that this scoreboard is